Hey guys, welcome back to the Transformer Slam series. This is going to be the episode 7, and this is going to be the last episode in the phase 1. Um, it was targeted for 3 weeks, but since we went into much depth for a few things, like for example, vision transformers and attention mechanisms and all that stuff, so it took longer than expected. And also, like, I have to, of course, uh, find time apart from my work for this. So sorry for the delay. But anyway, this is going to be the last episode. And in this episode, we will be creating a vision transformer. And then we'll be also visualizing the attention maps as mentioned here in the project plan. Okay, so without much delay, let's jump right into it. Last time we discussed about vision transformers, how transformers work. Um, in case if you guys haven't gone through the last episode, I highly recommend you to go through it because it gives a very good conceptual understanding of how transformers work and how the attention mechanism, the encoding and all of that thing, multi-headed attention and all that works. Okay, so coming back to this episode, we did discuss last time that since we already went into the theoretical depth of transformers, we wouldn't be applying, or we wouldn't be creating a transformers from scratch here. What rather I'm doing is I'm using a Hugging Face library to create the transformer model, and they already have pre-trained models, and use their model to do inference, and we'll also see some more detail about how that works. Okay, so starting off, we have I'm doing this as always in Colab notebook. So we have some installation of libraries. So I already have run it, but anyway, let's just run it again. I'll go through the code one by one to help you understand what's going on here. Okay, it's installed already. Now here are some imports. This line that you see here is for creating a processor that basically resizes and normalizes your image so that it is it's in the format that is expected by the pre-trained model that we have. And the next line here is the line, I mean, this line of code pulls the model from Hugging Face library, the model that we want. And here we have specified the name of the model. This is a vision transformer. And 224 is basically the image size that it expects, which has 16 patches, that gets divided into 16 patches. And we are putting the model into evaluation mode, model by doing model.eval here, because as I said, the model is pre-trained. We don't need to train it again. We just need to run the inference. So that's what we do here. Let's run this. Okay. So now we ran this section of our code, and it did pull the model and created the processor, and it gives some more information about how the model is created. So yeah, then moving on ahead, this we are using the um, the PIL library pillow to get the image from a URL. Okay, here we have defined the URL. It's also a Hugging Face URL. So basically, they have some libraries for data sets. So we are pulling from there, and then we are creating our image here. Then after that, uh, we we pass our image to the processor that we just created to process the image. And then with torch no grad we have here, because again, as I mentioned, we are not training, so we don't want any gradient updates and all of that, right? we 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 don't want to change any weights and anything. So with torch no grad output, we just run our model with our inputs, and then we get the output logits. Okay, that's what is happening here. So when we have our output logits, what this line does is that in the logits, so logits will have like a vector. Okay, so this one gives us the index of that particular logit where the value is maximum. Okay, why that happens is because that means that the prediction belongs to that class, so it has the highest probability of belonging to that class. We have done all of this again in previous videos, especially where we discussed about CNN and we created a CNN. So just go through that video in case you need some you need to revise. And then we get the label. So we get the prediction ID, and then the model itself, the model that we pull here, the model itself has an inbuilt lookup dictionary, which basically helps us in looking up which class does the prediction belong to. So since we have the ID, we look up in that dictionary and we get the class of what the object is in the image. Let's just run it and see. Okay, so prediction says that it is tabby cat. Let's see the image. This is just a simple matplotlib. Okay, so image has two cats in it. I just looked up, and this kind of cat, basically, which has this particular stripes, this design of stripes, that is called a tabby. So yeah, it is basically identifying correctly. Okay, so what we did so far, just a revision, is we used the Hugging Face library, which is this one, to create our image processor and pull a model, a ready-made pre-trained model. Since we are doing only inference, we put it in eval mode, and then we got our image. Okay, you can get the image from anywhere you want. We got it from URL, and then we pass that image to the processor to format it to be it in the way that model expects. And then we got the outputs of the model, and then we got our prediction class. Now we will get into checking the attention maps. Okay, so again, not much of a refresher. If you want to have a good idea about this, please check the previous video, especially episode 6, where we discuss about what attention is. But basically, when the model tries to learn the relationship between different patches of the image and try to understand where it should focus more to be able to better identify the image, so those in those patches, in those places in the image, the attention will be more. So we will try to visualize that. And for that, what do we do is that we use this line model set attention implementation. So this is an inbuilt method in Hugging Face that ensures that attention tensors are stored. Instead of just being used for calculations and giving the outputs, the attention tensors are also stored so that we can extract it and do the visualization. So that's what this line does. And then we get our outputs. Okay, and we get our attention maps and hidden states by again using the inbuilt methods that they have. So hidden states is nothing but it's basically features, Like when image passes through layers, some features are extracted, right? So these hidden states will have those extracted features for each passing through each layer. And then attention, same thing, attention maps after passing through each layer. So we're gonna have that. So here what we are doing is I'm trying to extract the attention from the last layer, because this gives the attention maps from all the layers. So I'm trying to extract it from the last layer, and that's why you see -1 here. And then I'm doing some like finding the mean, and then uh, uh, okay, here what this does is that when we have our tensor image tensor along with class the class token. So what this does is that it just separates out the class token, because class token is not really part of the complete image, right? So it separates out the vector for class token, and then we have our full main tensor that has the maps of all the attention within the image. So that's what this line is doing. And then I create a heat map out of it, and then I just plot the heat map. Okay, so let's just see how it goes. So this is our heat map, where it's showing that, any patch that you see that is more towards red side, there the attention is more, and if it is more towards blue side, then there the attention is less. Okay, but if you try to relate this patch to the image, it does not really make much sense, right? Because you see the attention is kind of here more, and then in some random places. But why that is happening is the attention that we get in the last layer is not necessarily the attention, the overall attention uh, that the model sees. Okay, what model sees is that a series of attention passing when it passes through all our layers, and the final attention is not just from the last layer, but it's kind of a cumulative attention from the from all of the layers. That's what uh, that's what is called as attention rollout. Okay, so instead of just seeing the heat map from last layer, now we will see the attention rollout and the heat map for that. Here I have a function to get the attention rollout, where this is not doing much but just iterating through all the attentions and then getting some mean and doing the dot product. Why? So if I had to explain that, um, mathematically what happens is, uh, for each attention map, okay, we average it out, okay, and then it is added, an identity matrix is added, and then again what you see here, rows are normalized, and then it is multiplied dot multiplication. It is multiplied layer by layer for all the attention. So if you see it mathematically, if A1 is the attention map from one layer, A2 is the attention map from another layer, so it is like A1 dot A2 dot A3 dot A4, like a chain rule. Okay, so that's what we are doing here. Again, you can see, just iterating over through it all, doing all the mathematical process that is defined here, and then doing the dot product of it all, okay, in this line. So we get the final rollout, and again we do the same thing for rollout. We extract the uh, the part of the tensor where it corresponds to the image, and then here we are just doing some normalization. We get the heat map and then we plot the heat map. So let's see. Okay, so we have got this heat map, kind of making more sense. We see it like towards the center, the attention is more, where you see the cat, and then also maybe somewhere towards the top. Now, just to visualize it better, what I'll do is I'll overlay this attention map on top of the original image. I'm not going to explain this code here. This code is just for the overlay part, not really much necessary to understand in terms of whole attention thing and how the vision transformer is working and all of that. So I'm gonna skip it. If you want, you can go through the code and you can try to understand it, but it's fairly simple, just the overlay. So I'm going to run this and see the overlay. Okay, and here we have our final overlay. We see that, in these parts the attention is more, where you see like green, yellow and red, and here like attention is very high towards the nose of the tabby cat, and then also on the body attention is higher compared to other places. Okay, so kind of really makes sense, right? So instead of having the attention from just the last layer, if we take the attention roll out from all the layers and then we try to relate it, we can see that okay, this does make sense. We can really understand where the attention goes. So this works correctly. Now all is this is working correctly, but one last thing that I would want to discuss more about is some fine tuning. So we saw that we utilized a pre-trained model, but what if we needed to do some kind of fine tuning, do some modifications for our particular use case? So what do we do in that case, right? So what we'll be doing is, of course, instead of having the model in the evaluation mode, we put it into train mode, we change the parameters. So for example, Hugging Face itself has options to change the parameters, where you can call it by model.parameters, and then you can specify a few things. Like in this case, I'm specifying the learning rate, I'm changing the learning rate. Also, I am specifying that we are going to be using Adam optimizer. So maybe the model uses SGD, stochastic gradient descent. So here I'm specifying that my model should be using Adam optimizer. And then I get the output logits. This is basically the forward pass. And what I do here is, once I get the logits, suppose I have a loss function. So in this case, just as an example, I have taken cross entropy loss as the loss function, and then I find the loss, and then I do the back propagation here, loss dot backward optimizer dot step, right? So basic training schedule, right? You do a forward pass, you find the loss, and then you do a back propagation and optimize. So that's how we can do the optimization, the fine tuning of this model. Also, if you wanted to add, suppose, a separate MLP layer at the end for better classification, then you could also do that, like create a separate uh, uh, class for your custom MLP layer, and then use that as the last layer. So after getting the outputs from the last layer, pass it through that, and then do a back propagation again, do loss calculation, back propagation. So you can work it that way. Just something I wanted to talk about. So yeah, I think that's about it for this last episode. I have tried to keep it short because we already discussed all the theories and the concepts previously. But yeah, from next week onwards, we will be trying to look at um, feature matching. So since we are already done with visualizing attention maps, getting vision transformers up and running, next what we have to do is we have to do the feature matching part, because that is really necessary for SLAM, and that's the part where we are trying to replace it with our transformer based neural network. So we'll get into that, and that's about it for today. Thank you, and please stay tuned.